All righty. And so now what I would like to do, so those are kind of a bare rundown of the different types of forces that we can run into. What I would like to do is I'd like to go over the Newton's 3 laws, and then we'll have, that's probably about as far as we're going to get for today. And so we'll actually start working on problems on Thursday. So let's go in and let's talk about our Newton's laws of motion. And there are 3 of them. Okay, so the first law, and I'm going to write this in kind of a compact fashion. We'll have that an object in motion, or we could also say an object at rest. So the idea is that the phrase inside this parentheses will replace the immediate phrase right before those. So, and then that way I can rewrite 2 sentences as essentially one. So we're going to make it like a compound sentence, I guess. So an object in motion will remain in motion. In a straight line. Or the object at rest will remain at rest. Until a net external force acts on the object. Okay. Now, this particular law is referred to as the law of inertia, and essentially was due to Galileo. Okay. And I think that Newton included it as the first law as an homage to Galileo. You know, Newton was quoted as saying, "If I have seen further, it was because I stood on the shoulders of giants." And so he usually did appreciate all of the work that went into our understanding prior to when he came onto the scene, such as the work done by Galileo. And Galileo did some really groundbreaking things because for, centuries prior to that, it was the views of Aristotle that held everything in place. And so according to Aristotle, then if you have an object that's moving, you had to apply a force in order to impel it to move. Okay. And Galileo was able to show that that wasn't necessarily the case, and he did this because he was placed under house arrest for the remainder of his life by the Catholic Church for ridiculing their position on the structure of the universe. So, that whole heliocentric, geocentric universe kind of argument that went on there. And so Galileo, being Galileo, went in to show that, well, Aristotle was wrong about other things also. So this was his effect, his work on that, to that effect, while he was in, under house arrest. So kind of idea. And so what Galileo talked about was that he did this, this experiment with a set of ramps. Okay. So he had a ramp, and then he rolled a ball down the ramp, and he noted that the ball essentially returned nearly as high as where he released it on the other side of the ramp. And then when he lowered this end, once again, the ball nearly reached the same vertical height as where he released it, even though it traveled much further. And then what Galileo argued was that if he never had it come back up, then the object would just keep on going. So an object in motion will remain in motion until you act on the object with some sort of net force. So again, one of the things that's really important here is that we're talking about net forces acting on objects, okay? So he was able to move to this position where he said that, well, if the ramp never came back up, it would just keep on going, okay? And so, yeah, this was Newton's first law. An object in motion will remain in motion in a straight line until a net external force acts on the object. Also, an object at rest will remain at rest until a net external force acts on the object. So it's actually two phrases written the way I wrote it in one, and that's fine. All right. And like I said, I think this was, in honor of the work done by Galileo, who came before him. Because in some sense, with the second law, you can see that the first law is a special case of the second law. And so did we really need it? And I kind of think no, but I kind of think the reason he put it in there was to, pay homage to Galileo. And so Newton's second law, and we've seen this one before, is written usually as the equation. This symbol here, this is a Greek letter, a capital Greek letter called sigma, and it means to add. So just like delta means change in, sigma means to add, and that's the capital sigma, and the lowercase sigma is that little other one. So you get the sigmas are the capital and then the lowercase. And we saw this with the standard deviation, okay? So yeah, there we go. And so this is our force. And so then what you get is when you add up all of the forces, then we get that this is our net force. And since it's a vector, you have to add them like vectors. So you have to do component work and put your x's with your x's, your y's with your y's, and so on and so forth. This m here, this is the mass, which is a characteristic of the object. And then this is our acceleration. Of the object. And so this was what we verbally talked about with free fall, was that if the net force was only gravity, so if there was only gravity, then gravity is the net force, and the acceleration would be the acceleration due to gravity, okay? And so from this perspective, then what they will talk about is that mass is a measure of the inertia of an object. Okay. And inertia is kind of an older term. And so what they mean by that is that inertia, they usually view as the ability of an object to resist changes in the state of motion. And when we talk about, changing the state of motion, then what we're talking about are accelerations. So an acceleration is any change in the velocity of the object. So that's a change in the state of motion of the object. So we're talking about the ability to resist being accelerated, okay? And so that's usually how they define mass. And when we do it this way, I don't think it's very I don't find it very easy to understand, kind of what we're talking about. So that's why I kind of like this idea that matter's made out of atoms, which are made out of particles that have certain characteristics, such as mass. And so when you look at the mass of your overall object, it's due to the mass of the individual bits and pieces that make up the object. And while you would think that if you knew how many protons, how many neutrons, and how many electrons were in the object, you could use the mass of each one of those to get the total mass of the object. But unfortunately, that's wrong. That ends up being more than the actual mass due to a concept called binding energy that we will talk more about in Physics 2 for those that take Physics 2. So, but it's the same basic idea that the more atoms and particles, the bigger the mass should be. So while it's not an exact kind of thing, I think that this, in my mind, makes it easier to understand what is the mass of the object. Well, that has to do with how many atoms and molecules are there. And that's a good statement, okay? The specifics of how to calculate how much mass is a little, there's problems with it due to binding energy. But in general, the more atoms, the more mass kind of things, okay? And so I think that's much easier for me to picture than this idea of being a measure of the inertia of the object, okay? And so what we can talk about is we can talk about if we were to go out to a parking lot and we were to go in and apply as a net force to a big truck and then see how much acceleration the truck would have as we pushed with our force on the truck. And then if we were to push with the same net force, but on a little bitty car, then we would note that there would be a distinct difference in the acceleration of the little car compared to the big truck. And what would we find? Well, how would the acceleration of the little car compare to the acceleration of the big truck if we had the same net force? So we were to push. Yeah, that's right. What you would get is that the little car should have a greater acceleration than the big truck because of the difference in mass. And that is this idea of inertia that they talk about. Okay. You would need, if you want the accelerations to be the same on the car and the truck, you need more net force on the truck than on the car because the truck has more mass. Therefore, it has more inertia. Okay. Okay. So I think that one's pretty visual, that if we applied the same net force to both, then the car accelerates pretty well, but the truck not so much. If we want them both to have the same acceleration, then we would need more net force on the truck than you need on the car. So I think that one's kind of visual. So I think that helps a little bit in terms of what is the mass. But again, this is Newton's second law and will be, extremely important to us when we set up and work our various problems. All right, now let me do the third law, and then we're going to call it good. And so Newton's third law talks about the fact that all forces come in pairs. These forces are going to be equal in magnitude and opposite in direction. So if we have a pair of forces that are equal magnitude, opposite direction, one would generally assume that what's going to happen to our object if we, in this instance. Yes, Boone, you're gonna need to know what they are. So I guess that means memorize. But you would need to be able to describe them. Yeah, yeah, manual's right. That, I mean, if the forces are equal magnitude, opposite direction, wouldn't they just cancel out or there would be no motion kind of things? But the answer is that's not correct because so they do not cancel. Or you could say, sum to zero. And this is because, well, in general, because they act on different objects. Did I answer the question, Boo? So the thing that we have, oops, where's my picture at? Go here. These two normal forces, these are third law pairs, is how I usually call them. A lot of people refer to these as action reaction pairs or action reaction forces or whatever. But yeah, so what you get is one of the normal forces is on the box, but then the other normal force is on the table. And so because they act on different objects, they don't necessarily cancel. Because what will happen is we're going to go in and analyze all the forces on the box only. And so you'll never see the force on the table that's the third law pair to that normal force on the box. And so that's really part of the big reason for why they don't, in general, cancel or sum to zero. Okay. Now, one thing we do need to talk about is we need to go in and note that the converse of this statement, the third law, Newton's third law, is not necessarily true. Okay. And you're like, the converse, what do we mean? So that means that if we talk about two forces that are equal in magnitude, opposite in direction, that they're not necessarily third law pairs. So two forces that are equal magnitude, opposite in direction, are not necessarily third law pairs. Okay. Have a bad analogy. Okay. The analogy is about twins and their birthday. So as a general rule, what would you say about the birthday of twins? I kind of gave that away because I said it wrong. the birthdays of twins. Yeah, as a general rule, it should be the same day, right? Twins are born on the same day. Now, I'm sure there are examples of one twin born on, before midnight and the other one born after midnight. And I think this year there was a story about twins where one was born last year and one was born this year, right across the New Year's Eve kind of thing. Okay. So if the statement is that twins are born on the same day, I'm sure that one's never going to let the other one forget that. That's going to be the way that goes. I can see it now. So if twins are born on the same day, then the converse would be two people born on the same day, are they twins? And the answer is, well, no, not necessarily. Just because you have the same birthday doesn't make you twins, right? I mean, they kind of have other requirements, like, I don't know, they have the same mother or something like that. There has to be other characteristics to guarantee that they're, in this case, third law pairs, or in that case, twins. Okay, so let's talk about what will happen. So the rules are that to be third law pairs, then our forces, number one, have to be the same type. Okay, so have to be the same type of force. So both gravity, both normal, both friction, both tension, both the same type. And then the second characteristic we need is that essentially the on and the by have to trade. If these things are true, then they're third law pairs. Let's go back to our normal forces in the little picture. Where did I put that? There we are. So I got my box on the table. And so we had the normal force, and this was on the box by the table. And then I had this normal force on the table by the box. So number one, they're both normals. Okay. Number two, the on and the by trade. This was on the box. This one is by the box. This one is by the table. This one is on the table. And so the same type, the on and the by trade. So that means these two normal forces are third law pairs. So that means they're going to have equal magnitudes and opposite directions. We can see they're in opposite directions, but it means the magnitudes are going to be equal. So, questions? This will come up in the lecture on Thursday. I guarantee you, whether two forces are going to be third law pairs or not. I'll tell you right now, if you answer incorrectly, I'm going to ask when your birthday is. And I'm going to tell you it was the same day as mine, and then ask if we're twins. So, just as a heads up.